Okay.
Recording in progress.
Okay, so now let's see what other factors really influence this separation and how we can play with the mobile phase and then to achieve separation that we want. So let's start with from the resolution. Okay, so you have shown that again. So before we show that already. So we say, let me see. Sorry, guys. So resolution equal to the square root of n number, the plate number, and this also so plate number also relate to the selectivity factor alpha and also the retention factor. Retention factor, we write it in k over 1 plus k. So that is capacity factor, we call that. So this is, you have learned that from the gas chromatography, right? Okay, so the plate number, we see how that influence so the resolution. So if we plot that one, you can see that. So the plate number, so because it takes the square root, right? Okay, so that's why. So it's not compared with alpha and k. So it's the least rewarding factor for us to increase that resolution. So probably, so when you are thinking about this one, so there are 3 terms for us to play with. The plate number, this one, most of the time is really related to the packing, right? The packing material, the column itself. If you already have that column, okay, so and you want to optimize the condition, and then so what you can think about more is like say how we can play with k and alpha, and then so if we, for example, if I already select the column with the fixed packing material with the DP already there, and then because we know the n number is really related to the DP, right? Okay, and those things, and then so that's why. So if you want to play with the mobile phase, and then so then you need to think about how you're going to use the mobile phase to adjust the k number and also the alpha selectivity factor. Okay, anyway, so let's look at the selectivity factor first, because we mentioned the selectivity factor alpha equal to so k2 over k1, the ratio. So when the alpha equal to 1, so that means these 2 peaks have the same k value. That means they are overlapped. There's no separation. So resolution, if we put here alpha equal to 1, so this term equal to 0, so that means no resolution, not separated. So you wanted alpha to be larger than 1, so k2, the one eluted after k1, and then so separation can be possible. If we put the number in, we can see that when alpha equal to 1, so this term, the selectivity factor equal to 0, but when equal to 2, and then 2 is equal to 0.5, right? It's here. Okay, so here's a 0.5. If equal to 4, okay, and then it's already equal to here, so this 0.75. We can see that. So when the alpha, so it's between 1 and 2, so a change of the alpha can really increase so the resolution is a lot, right? Okay, because this change is most obvious and dramatic. So between 1 and 2 here in this region. So when alpha equal between 1 2, so the resolution is the most rewarding. We change that. So think about it. This is the number, okay? And then so how about k? How about k value? Because now resolution related to the capacity factor, which is k divided by 1 plus k. We also know that the retention factor, we have shown you guys for many times, is equal to TR minus T0 divided by T0. So, and this shows you the larger k, that means it takes longer time for the compound to come out, right? Okay, so let's see, when we have different k value. So how about when, so the k value, so is equal to 1. Okay, so if k value equal to 1, and then so that is 0.1 over 2, so that is 0.5. So here's 1. Okay, so how about k value equal to 3? And then that is already 0.7, right? Okay, so we can see that it's actually quite increasing is this area. Okay, so and the k value from actually I can say from 0 to 1 is pretty rewarding, but as we mentioned that for most of the separation, so you don't want, because if a k equal to 1, what does that mean? If k equal to 1, what does that mean? So for example, okay, so it just give you an idea. So in case, if you have a t0, for example, if you have t0 equal to 1 minute, okay, so this is where solvent comes out. So when you have a compound which has a K1 value equal to 2, so what is the TR1? Anyone tell me? Can you type your answer? So in the chat box, if it's K equal to 2, and what is that? So that means TR1 equal to how many minutes? 3 minutes, right? Okay. So, but if KR2, the second peak, equal to 10, what does that mean? That means the TR equal to what? TR2 equal to 11 minutes, right? Okay, so that means say for the compound, if the first compound comes at, you will have a K value of 2. So if T0 equal to 1, so that means it comes out 3 minutes. And then the last one, so if it's K or 10, so it comes out 11 minutes. So they are apart from each other. So that means like say, even the K value, so before like say smaller than 1, it seems like very rewarding. But that makes what? That makes the peak comes out very, very early, and then everything squeezed out at very beginning of the run. Even you see, because like for this one, when k equal to 2, so it's already just at 3 minutes. So if k equal to 1, so that is even smaller, right? Okay, just 2, right? Okay, so that means everything comes out at very beginning of the run. So they cannot be well separated. So that's why for most of separation, so we aim to have the k value of the multiple, because you're going to have multiple peaks come out. You're not just analyzing one species. We aim to have the k value between 2 and 10. Okay, so that means we aim to have the k value for the lost compound around 10. But however, in some like food samples and environmental samples, they may be very complicated. So it's reasonable to have this k value to between 0.5 to 20 to make it to have enough range, to have enough for all the compound to be separated and comes out. Okay, so but then the question is, so how can we play with the k? How can we play with the k? Remember what we talked about just now? Why are we talking about this one? How can we play with the k? And this reverse phase and normal phase chromatography. So what did we do? We play with what? If we already have the column, so we play with the polarity of the solvent, right? Okay, so the most easy way actually to play with the k value is just to manipulate what? The composition of the mobile phase. And of the n number, we know the n number is really related to the column, okay? So, and so you have to think about the DP and all these things. It's not really, you have to buy the new column if you want to change it and switch. And alpha, this one is related to K. So this is related to K, from K. And then, so that's why the K value itself is the most easy one to manipulate. And as I showed you before, so we can actually easily change the composition for a mobile phase. And then that means polarity. And then we are able to change the K value, okay? So, and well, how about for alpha? After we change the K, And then so for alpha, also can be played with this mobile phase. And we can play with this composition as well. How to do that, I'm going to show you later, okay? But while we're doing the change the alpha, we have to make sure. So because first thing for you is to adjust the K. So after you adjust the K, for example, you make it to be a very nice one, to be a nice range about 10. So you want to keep it, the 10, the K value unchanged. And now you play with the mobile phase composition and you see whether you can change the alpha, okay? So, and also, if you change the mobile phase, still cannot achieve a very good separation, and then you can think about whether you should change the column as well. So that's another option. So how can we do that? So we basically use that polarity index. So what is a polarity index? Polarity index is because the successful chromatography, so really depends on the interaction of the analyte between the mobile phase and also the stationary phase. You have to have a proper balance of these intermolecular forces among these three phases, three participants: analyte, mobile phase, and stationary phase. So I've been talking about that for so many times. I say this relative distribution, so really influenced by polarity. So this relative distribution of the analyte between the mobile phase and stationary phase is greatly determined by the polarity of the sample and the polarity of the mobile phase and stationary phase. It's not the only factor, but it's a very important factor. Okay, so the polarity of the various analyte functional group, so we already see that, already showed you guys. Say like carboxylic acid, most polar one, is more polar, so the amides, and then so the alcohol, ketone, and ester, and so on, and then hydrocarbon. And remember that water is polar than all this functional group. Okay, water is more polar than all those compounds containing this functional group. So therefore, once in choosing a column for a particular chromatography separation, the polarity of the stationary phase I mentioned should roughly match the polarity of the analyte. And the mobile phase is considered to be different polarity. This is what we have mentioned while we are talking about reverse phase and normal phase chromatography. Okay, now, and we use polarity index to show the polarity of different solvent. Okay, let's take a look about the common properties of this mobile phase. You can see we can have a wide range of polarity index. The most polar solvent is who? It's water. And then least polar solvent is fluoroalkane. So we can see the polarity is ranging from -2 to 10.2. So of this compound. And this one also shows the viscosity of the one. And this one shows the elution strength. That means the elution power for that one. So, but anyway, we can see that so what does that mean? So it means that for the mobile phase, so we can actually, because you know that when for the HPLC mobile phase, we are not just using one single solvent as a mobile phase. We often have phase A and phase B, right? Okay, so if we're doing the gradient elution, you have phase A as water and buffer solution, and phase B is organic phase. You are actually changing the percentage of the water phase and also the organic phase. Why is that? Because by mixing different portion of the water phase and also organic, you are able to adjust the polarity. So within the range of -2 to 10.2. That means, so by combining different solvent together, so you can reach any desired polarity index between this limit. Okay, so and how to calculate that? That's very easy. So the polarity index of the mixed solvent, which say polarity AB prime of the mixture solvent A and B, we can calculate by using this equation. So where phi A is the volume fraction of solvent A P prime A is Polar index of solvent A. So phi B is volume fraction of solvent B, and B prime is the polarity index B. For example, what is the polarity index of solvent mixture of 50% of methanol and 50% of water? The first thing for you is to find the polarity index. The polarity index of water equal to what? 10.2. Okay, everybody should remember that already, right? How about for methanol? Can you go to the previous slide? So you can go to find it. So how about for methanol? What is polarity index? Methanol 5.1. Okay, so methanol is 5.1. 5.1. So how to calculate that? Now we know polarity index A, polarity B, and we know the percentage is 50%, 50%. So it's just like say, so the overall polarity of the mobile phase now is 5.1 times 0.5 plus 10.2 times 0.5, which is 7.65. This is the overall polarity index of the mixture solvent. Okay, so how about now I have 50% of ACN plus 50% of water. So what is the polarity index of this solvent? Type your answer in the chat box, okay? So how about you try that by yourself? Or yeah, how about that? Yeah, okay, good. 8. Okay, very, very good. Okay, 50%. Oops, sorry. How to do that? Very easy, right? So what is the ACN? 5.8 times 0.5 plus what? Well, 10.2 times 0.5. So that equal to 8. Very good. So you know that. Okay. So how about next one? So we see that because already, so from our understanding, we show you guys the peak ABC, right? From ABC, we show that again, ABC, compound A, compound B, compound C, and then the illusion, we already see that. So we found the power index can really influence the K value. And the influence of P on K is different for normal phase and for reverse phase. And we already see that for the reverse phase, if we increase the polarity of the solvent, that increase what? That increase the K. Because what? Because the reverse phase, stationary phase, nonpolar. So if you want to elute the nonpolar compound out, so you have to use less polar solvent to do so, right? So that means if you use more polar one, well, it will stay in the stationary phase and then the K increase. But however, for normal phase, if we increase the polarity of a solvent and then the more polar compound eluted out faster, the K decrease. So we have empirical equation. So we can describe a relationship between the K value and the polarity. Okay, for example, in a reverse phase chromatography, so the ratio of when we change the polarity of the solvent from P1 to P2, okay, and so the retention factor increase, and then so it can be K1 over K2 over K1 equal to 10 order of P2 minus P1 divided by 2, that order, okay? So, and then so how about for normal phase? So, and because P increase, K decrease. So that's why, pay attention here. So here is P1 minus P2, okay? So what we see that is when P value, if the P value increased by 2 units, so that means this part will increase by 1 unit, right? If it's exponential, this one increased by 1 unit, that means the K value will increase by 10 times. Understand? Okay. So the easy way is often to do an exercise together. So now let's see one exercise. There is the first question. So in a reverse phase column, a solute was found to have retention time of 31.1 minutes, and unretained species required 0.48 minutes for elution when the mobile phase was 30% by volume of methanol and 70% of water. Can you calculate the K value for this analyte, for this solute? And also, can you provide a water methanol composition that can bring the K value to about 5? Okay, 2 questions. First one, you have to know K. Okay, so again, we already know. Don't look at the answer first. Try to do that by yourself first. K equal to what? TR minus T0 divided by T0. Now, do we know T0? Anyone can give me the T0 in the chat room? What is T0? Anyone can give me the T0 number? T0 means the compound not retained, right? Okay, very good, very good. So T0 equal to, oops, sorry. T0 equal to 0.48. And then how about TR now? What is TR? What is TR? TR is, can anyone tell me the TR? Yes, very good. So 31.3. Let's put it, oops, 31.3 here minus 0.48. And we can calculate the K value, which, what's your answer? I got 64, okay? So we got 64, already got 64. Okay, now we know the K value. Okay, so we answer the first question. Now, it says like, okay, the second question is like, say, now we have the 64. I want to bring the K value to 5. So that means now I have K1 equal to 64. I have K2 equal to 5. Okay, so, and it's reverse phase. Can we go back to the previous slide? What is that equation? What is that equation? K2 over K1 equal to 10 exponential what? P2 minus P1 divided by 2, right? Now we already know K2, which is 5. We already know K1, which is 64. We need to know P2 and P1. All right, okay. So first one, can we know P1? Can we know P1? Can we know P1? Yes. Okay, how to do that? Because we already know 30% methanol, 70% water. So that's why we already checked the methanol. So for that one, what is the methanol one? It's for P1. Okay, so we already have it. Methanol, we have it, right? If you go back to here, 5.1. So always go, you can go back to this table to find it. Okay, water 10.2. You already know that. Okay. So then you have to 5.1 times 0.3 plus, oops, so 10.2 times 0.7. And now you have the p-value equal to 8.7. That's for P1. Okay, now we have P1. Can we put that into this equation? And now then we can know P2, right? Okay, so that is good. Now we put in, because 5 divided by 64 equal to what? Equals to 0.078. Okay, that's what I get. So, and because we want to know P1, how about we take log of both sides, right? Log 5 over 64 equal to P2 minus 8.7 divided by 2. Then I got what? I have log, so point of say minus, I got minus 1.11 equal to P2 minus 8.7 divided by 2. And then for that one, so that is 2.22, 8.7 minus 2.22 will be P2. So P2 equal to 6.5. I just like say, so I just rounded to one significant factor. And then now it comes to a point. Some student got confused here. Say, only P2, but now you ask me about composition. How can I know the composition? Okay, so we just set x to be the what? X be the fraction of what? Fraction, we can say that x to be a fraction of methanol. How about that? Okay, because we only have two solvents mixed together. If methanol is x, so how about water? Water will be what? 1 minus x, right? Okay, water will be 1 minus x. So what we do is like say, oops, 6.5 equal to what? Equal to x times 5.1 plus 1 minus x times 10.2. And then from that, we can know x equal to 73%. Okay, so that is how we do that. Understand so far? Understand now? Okay, so if you understand, I really want to know you really understand or not. So anyway, so this is the solution for that. Because for this one, I provide you the answer. So then that's why I give you extra question. Now I have an extra question. I will give you 5 minutes and then you can type your answer in the chat room. Okay, so now it's normal phase partition column. The solute found to have a retention time of 32.8 and an unretained compound required 0.8 minutes for elution when the mobile phase was 20% chloroform and 80% N-hexane. Calculate the solvent composition that would bring K value to 10. I give you the polarity index of chloroform and N-hexane to be 4.1 and 0.1 respectively. Okay, so now it's your turn. Can you do that? Okay, so 5 minutes. So after that, you can provide me the answer in the chat room. So if you're shy, you can directly send to me, or if it's fine to share with everyone, so you just share with everyone, okay? So try it yourself, 5 minutes. Anyone has done? I did calculation myself. If you have an answer, let me know. Percent of chloroform and percent of N-hexane. First, we always need to calculate K, right? Can anyone tell me the k-value first? What is the k-value? K-value? Equal to 32.8, right? Oops, 32, thank you. I got a bit different. Minus 0.8, which is 32, divided by 0.8. Yeah, I got 40. Same, thank you. Thank you for answering my question, both of you, thank you. I got 40, okay? So how about, we already know K, how about P1? Okay, can anyone tell me what is the P1 value? Sorry, it's keeping rotating. I got 0.2 times 4.1 plus 0.8 times 0.1, I got 0.9. Okay, thank you, very good. So we got same answer, right? That is very good. And we will write down the equation, right? Because now it's normal phase, guys, it's normal phase. So K2, K1 equal to, jump into my screen, quite sensitive. P1 minus P2 divided by 2, right? Okay. Because now, what is the K2? K2, 10, right? So we can get 10 over 40, P1 over P2 equal to 10 to the minus 10 to the order exponential. Okay, 0.9 minus P2 divided by 2. Let me see the answer. Okay, close. Okay, maybe I just like say get it to very narrow down. So I get this one. What's your P2 value, guys? Yeah, answer is very close. P2 equal to 2.10. That's what I get. Did you guys get same? Oh, okay, very good. Happy to see that. So we got 2.1. Okay, now again we set. So which one to be X? I set chloroform to be X. Okay, so it says chloroform to be X, and then so hexane to be 1 minus X. Now I have P2. So 2.1, which is P2 equal 2.1 equal to 4.1 times X, because this chloroform, right? Polarity index, plus 0.1 times 1 minus X. Okay, and then so that found, anyone can tell me X. What is X? You have? Yes, very good. We got the same answer, so happy, right? Okay, so we got 50%. So this is 0.5. So that's why, so it means 50% of chloroform and 50% so of hexane, okay? So N hexane. Okay, so great. It's good that we do this exercise together. So you from that, you make sure, so you understand, right? Okay, so that is very good. I guess that's pretty enough for today, right? So we have this one, and then so I think if I keep talking for another 4 minutes, maybe don't make any sense. So let me see. So because later on we are talking about how we play with K, and that will be a long story, because then we talk about the figure, you see A, B, and then so we talk about the story will be C, D, E. Okay, so we'd better to describe that or discuss that. So next week at the very beginning. Okay, so that is all for today. So guys, if you don't have question now, so so that's the end of today's class. Okay, so I will see you guys again so next week, and take care of yourself and stay healthy. Okay, so protect yourself. Bye bye.
Dr. Hu, excuse me, I have a quick question. I want to ask for the atmospheric and pressure chemical ionization. You mentioned that we should not use the buffer inside the analysis.
As low as possible. Yeah, try to as low as possible for APCR.
As low as possible. The
Yeah.
amount as low as possible.
Yeah, so because sometimes it cannot really avoid that one. So it's not, so then you try to do that as low as possible, because then it makes it so quite polar if you make your compound ionized, and then so more difficult to evaporate, you know. Yeah.
Okay, thank you.
That's a point. Okay, so
okay, thank you.
You're welcome. Any other question? If no, so that's all. Bye. Let me see. Stop sharing.